UDP, or User Datagram Protocol, is a Layer 4 protocol. This protocol is responsible for transport and will provide sockets-based connectivity with connection limitations. What I mean by connection limitations is a message boundary. Typically with UDP applications will have a message boundary since no session is established prior to sending data. This means most of the time packet by packet conversation is done. Typically, UDP conversations are broadcast or multicast based, and it's one of the main attributes of the UDP protocol. The UDP protocol provides applications with access to the network layers where IP runs, without the overhead of any reliability mechanisms, meaning that it has the capability of being very, very fast. Because IP itself is connectionless, a UDP combination with IP conversation can be one of the quickest conversations out there in the TCP/IP world. Because it is connectionless and has limited error checking, it's going to use best effort delivery. However, UDP does not have any data recovery features. If you have an application that utilizes UDP, such as the Trivial File Transfer Protocol or DNS lookups, it will always be a responsibility of the upper layer application to provide these data recovery features because UDP does not provide them by itself. However, the TCP protocol provides all of these data recovery features. TCP, or Transmission Control Protocol, operates also at the transport layer, and this is one of our choices when writing applications for TCP/IP. It provides applications with access to the network layer as UDP does, but it is a full connection-oriented protocol. This means that a session is established prior to sending any actual data in the application's conversation. TCP has a full duplex operational mode and provides error checking and sequencing of data packets along with acknowledgement of receipt. It includes full data recovery features including sliding windows buffering. TCP does not have any message boundaries because a session is established at the beginning of a conversation and the session is destroyed at the end. This is accomplished through a three-way handshake process, which guarantees synchronization between the two hosts that are part of the conversation. The hosts will then be able to send any amount of data inside of that conversation with no message boundaries whatsoever, and all of the data packets will be acknowledged. They'll be able to operate in full duplex and can always be received out of sequence during that conversation, and can always be resequenced by the receiving hosts. These are some of the features of TCP-based applications. Applications such as World Wide Web, FTP, or even a DNS zone transfer have the ability to establish a session, send data with no message boundary, and tear down the session at the end, all the while guaranteeing that the packets are received by using acknowledgments. When you're trying to master the TCP/IP protocol, a few things are very important to understand. Number one, when an application needs to utilize either TCP or UDP, it's actually a function of that application. It's not something that you get to choose. So when the application is written, it will decide whether or not to use the TCP transport or to use the UDP transport, based upon the requirements of that application. Number two, it's not a choice whether or not to use the IP protocol. All applications must use the IP protocol. The IP protocol covers the entire layer 3 of the OSI model. So when we are mastering the TCP/IP protocol, it's very important to understand the IP packet delivery process. Let's look at the IP packet delivery process. A host will first send a packet to its default gateway. The packet will then be placed in the frame. If you notice, we're dealing with the network and the data link portions of the OSI model. So we are actually sending data to the default gateway, which is usually our closest router. This is how we're going to be delivering data to a remote network. The packet itself will be placed into a frame at the data link layer, and this will then be passed across the physical layer where a router in between will receive the frame. The router will use its route table to choose the next hop towards the destination. It will find the destination in the table, choose the next hop, and then identify what the MAC address of the next hop is. Notice that this happens at layer 3. Routers run the IP protocol in the same way as the IP hosts run the IP protocol. And in fact, an IP host has the same intelligence as a router, but a router will typically have a bit more capability. It will be able to run routing protocols, and it will do things at just a little bit more optimal level than a PC. Finally, once the MAC address of the next hop is determined, the packet will be placed in a frame. It will then repeat steps 2 through 7 as necessary to get all of the packets towards the destination. Once the final router receives the frame, the router will find the network to which it is directly connected. The MAC address of the end host is determined by using ARP, and finally the packet is placed in a frame to the final destination. What we notice here is that all the while, from the original transmission of the data through every router and every ARP process, we never have to cover anything above layer 3. Layer 4 is not even contacted until the final destination is reached, and only at that point will any data that is placed inside of a frame for the destination application ever be passed above layer 3. And that's a very important aspect of the packet delivery process. You can also look at the IP datagram itself to identify some of the different bytes and options that exist inside this. We see version, identification, time to live, the service type, and the protocol that is requesting. We also see the source address, the destination address, and the various options. We see the packet length and a flag. The flag is used for fragmentation control and is actually sitting next to the fragment offset, which allows us to identify the fragments in a packet. We also have a header checksum, which is used to verify that the header is received intact, and if any padding is required to make the packet header itself the same size every single time. Now this is only the IP datagram header, which does not include the layer 4 through 7 data that would be coming through the application. This is literally just the header that is added at layer 3, but it does contain enough information for the IP protocol to properly move the data toward its destination, to receive the data at the destination, and to properly process it according to the right protocol once the data is received. That's what the protocol field is for, so it can pass it up to the appropriate transport. The protocol field itself is very important because the protocol field identifies the actual protocol that is going to be used or that is requesting the service. In some cases, it's going to be a TCP port, so we will actually see the TCP protocol field or protocol number 6, or the UDP protocol field or UDP number 17. The idea here is that the IP protocol will simply pass information up to the TCP transport if the protocol field is identified as being number 6. Once the information is passed there, the layer 4 through 7 data can be extrapolated. We can identify what TCP port is being used, that is, which application is being accessed or which application is being called. The same thing goes for the UDP protocol field. If 17 is identified in the protocol field, it simply passes the data to UDP and then lets UDP handle it from there. ICMP always has protocol identifier number 1, but other types of applications can also be assigned their own protocols, which allows them to bypass specific ports for TCP and UDP access. One good example is Cisco's routing protocol, the Enhanced Interior Gateway Routing Protocol, EIGRP. This utilizes protocol field number 88, which means that it does not require a TCP port for all of its conversations. It can actually use raw IP for much of what it does, which allows it to use IP multicast natively. One of the most common protocols that we have inside the TCP/IP suite is the Internet Control Message Protocol, or ICMP. ICMP is actually a multifaceted protocol, which provides a lot of support for our conversations within TCP/IP. It can announce network problems by identifying a destination unreachable. This could be a destination host unreachable or a destination network unreachable, depending upon what is being asked for. If I am sending a packet to a network and it is a network broadcast, a destination network unreachable can be generated by a router and sent back to me so that I know there is an issue reaching that network. If I'm trying to gain access to a target host, an ICMP host unreachable message can be sent back to me indicating that the host is not available. In addition, ICMP will announce network congestion by utilizing what is called a source quench. One of the very important aspects of TCP/IP communications is that applications that use TCP like to use buffers to be able to send as much data at once as they possibly can, or only require a single acknowledgement for a full buffer's worth of information. This can speed up the conversation with TCP/IP. One of the issues with buffers is information being sent too fast, where data being received by the target host does not have enough buffer space to be able to receive all the packets. This issue is solved by ICMP. ICMP on that target host can send a source quench message back to the sending host to tell it to slow down its transmission rate, because anything outside of its possible buffer space would have to be discarded and would have to be retransmitted. It's very important for a protocol to exist in the suite that can help us control such network congestion issues. It will also assist in troubleshooting by executing echo requests and echo replies when we use the ping command. In addition, the ICMP protocol can announce timeouts, such as when a protocol's time to live has been exceeded. Another major player in the TCP/IP game is the ARP protocol, or the Address Resolution Protocol. The idea behind address resolution is that I can't communicate across the network without a pair of MAC addresses, my own and yours. Somehow, some way, we've got to find each other's MAC address, even if we're on different segments. If we are on the same segment, I'll simply send a broadcast directly to you that will indicate that I'm looking for the MAC address of this IP. If you hear this ARP broadcast on your local segment, you will identify, hey, this is me, here's my MAC address, and you'll send back a reply. This allows my ARP cache to be updated with your IP and MAC address information. At the same time, it allows your ARP cache to be updated with my IP and MAC address information. At this point, we have mutual information, which is necessary for communicating at layers 1 and 2. If there were a router in between, it would be my job to ARP to the router and the router's job to ARP to you. Once this has taken place, all three of the systems in that equation would have mutual information that will allow us to communicate at layer 2 and at layer 1 because layer 2 is known. On a Windows platform, you can actually display your ARP table by looking at its contents with a command, ARP space -A. This will actually show you any static or dynamic internet addresses to physical address mappings that you have. You will notice that in this particular display, all of these are dynamic, meaning that they've all been built based upon network conversations. Static entries can actually be added as well with the ARP space -S command and then entering the IP address followed by the MAC address of that system. And the ARP table can be cleared with the ARP space -D command. You can individually clear individual records by using the ARP space -D and then specify the individual record itself, which includes the IP address and the MAC address of that record.